For this calculation, we are given a beam which is 8 meters long, where there are 3 downwards forces, a 2 newtons, 3 newtons and 1 newton force going downwards, and 2 unknown forces going upwards, which is reaction left and reaction right. We need to keep in mind with these type of calculations that all the beams are considered to be in equilibrium, which means that the sum of the downwards forces will be equal to the sum of the upwards forces. The downwards forces in this case is 2 plus 3 plus 1, which is 6 newtons, which means that in the end reaction left plus reaction right also has to be 6 newtons. So we can already make a note for ourselves over here. The downwards forces, the sum of the downwards forces equals to 2 plus 3 plus 1, which equals to 6 newtons. Okay. Later, well, we're going to calculate now reaction left and reaction right. After we've calculated them, we check whether the sum of these two also equals to 6 newtons. If we see that the upwards and the downwards forces do equal to the same value, then we are guaranteed to have most or all of the marks up to that point. My suggestion is if the sum of the upwards forces and the downwards forces does not equal to each other, that you restart and redo the calculations until the upwards forces and the downwards forces equals to each other. The reason for this is because normally the marking process does not allow for marking with a mistake. So if there was a mistake made at a certain point, we cannot mark with a mistake, which means that the rest of the activities that you did with a mistake was basically useless. It doesn't count anything or doesn't count marks. Okay, so use the advantage of checking whether the upwards forces equals to the downwards forces. Okay, so the beam is given to you, which is 8 meters wide. And the first thing that we normally are asked to do is to calculate reaction left and reaction right. Important here is that in order to calculate reaction left, we have to work around reaction right. And to calculate reaction right, we have to work around reaction left. So let's first calculate reaction left, which means that we are going to calculate the moments around reaction right in order to calculate that one. So the first calculation, we are going to write down the heading where we are going to work with the moments around reaction right. Okay. So again, we are working with the moments around reaction right, but we are actually calculating reaction left. Okay, so if it says that we are working around reaction right, that means that this is a turning point, it's a pivot point, which means that the beam basically where it lies like this, there it's the pivot point, which means that it's tilting either upwards or downwards here, either clockwise or anti-clockwise. Okay, so the upwards forces, or in this case there's only one force, times the distance of 8 meters, 2 plus 2 plus 2 plus 2, is the clockwise moment. So it's RL times 8 in brackets, RL times 8 meters equals to, that is the only moment forcing this beam to go clockwise. If there was more than one, we would have added them together here, but in this case it's only one. So that's why we say in brackets reaction left times 8 meters equals to the sum of the downwards moments. What I forgot to mention over here, as you can maybe make a note for yourself, is that the moment equals to a force, which is in newtons, times a distance, which is in meters. It's important that you remember a moment's unit will be Newton meters, because it's a force times a distance. Okay, going back to this, we have put in the brackets the clockwise moments, and then we say that equals to the sum of the anti-clockwise moments. So the anti-clockwise moments, here it's our turning point, it will be this force times this distance up to the turning point, plus this force, the 3 Newton, times the distance to the turning point, plus 1 Newton times the distance to the turning point. So it's 2 times 6, plus 3 times 4, plus 1 times 2. Putting those individual moments in brackets, which then will be 2 times 6, 2 Newtons times 6 meters, plus 3 times 4 meters, 3 Newtons times 4 meters, plus 1 Newton times 2 meters, 1 Newton times 2 meters. This will then be 12 Newton meters plus 12 Newton meters plus 2 Newton meters, which equals to 26 Newton meters. RL times 8 equals to 26 newtons. We still need to calculate RL, which means where RL is multiplied by 8, we need to divide by 8 on both sides. So actually it looks like this. RL times 8 meters equals 26 Newton meters. So because it's multiplied by 8 on the left side, we want to get rid of it. We're going to divide by 8, divide by 8. So therefore RL equals to 26 Newton meters divided by 8 meters, which then equals to RL equals to 3.25 newtons. Because the meters cancels with the meters, it's Newton that's left. And remember, we are busy calculating the force reaction at the reaction left. Okay, so there is our reaction left answer. As soon as you've calculated this one, you can label it here at reaction left equals to 3.25 newtons. Okay, now we're going to do exactly the same, and but vice versa, meaning that here we were working with the moments around reaction right to get reaction left. Now we are going to work with the moments around reaction left to get reaction right. So the heading will be moments around reaction left, which means that our pivot point or turning point is at reaction left. Okay, so working around reaction left, this is what our beam will be, the direction that it will be rotating in an anti-clockwise and clockwise direction, because the turning point is at reaction left, moments around reaction left. Okay, so the upwards force times the distance will be RR times 8 meters in brackets, equals to the sum of the clockwise or the downwards moments. So the downwards moment will be 1 times 6 meters plus 3 times 4 meters plus 2 times 2 meters. Each of these drawn in brackets but added together outside the bracket. So it's 1 times 6, 1 Newton times 6 meters plus 3 times 4 plus 2 times 2. That's 3 Newtons times 4 meters plus 2 Newtons times 2 meters equals to 6 Newton meters plus 12 Newton meters plus 4 Newton meters, which equals to 22 Newton meters. Okay, and this is still standing as RL times 8 meters equals to 22 Newton meters. You need to get rid of the 8 meters, So because it's multiplied by 8, we divide by 8 on both sides, which makes it that RR equals to 22 Newton meters divided by 8 meters will then be equal to 2.75 newtons, because the meters cancels out with meters. It's 22 divided by 8 in newtons, it's 2.75 newtons RR. Okay, so now that we've calculated reaction right as 2.75 newtons, we write it over here as 2.75 newtons. Okay, so now we've calculated reaction left and reaction right, which is 3.25 newtons plus 2.75 newtons. If we add these together, these are upwards forces. The upwards forces, the sum of it will be equal to 6 newtons. The sum of these two equals to the sum of these three forces. The upwards forces equals to the downwards forces. So at this stage, check whether the upwards forces equals to the downwards forces. If this works out, then you are guaranteed to get with this 1, 2, 3, 4 marks. The 3 marks are for the values within the brackets, but the plus signs outside the brackets, and for the final answer, so that equals to 4 marks. The same with calculating reaction right, where moments around the reaction left is considered. The 3 values within the equal signs will be each a mark, and the final answer will be a mark, which equals to 4 marks at this stage. Okay. Now that we've calculated everything surrounding the beam, all the values are known, and that we've checked them, the next question will normally be calculate the shear forces for all the points around the beam, which will normally then be point A, point B, C, D, and E. Just be careful, sometimes A is over here instead of there, then it will be calculate the shear forces at reaction left, A, B, C, and reaction right. But in this case, A will also be reaction left, which then is calculate the shear forces at points A, B, C, D, and E. Okay. So let's label our calculation, or give it a heading, where we are going to calculate the shear forces. And this is normally in newtons. That's the unit that we use for forces. Just be careful, especially in grade 12, they might give these values in kilonewtons. You can choose whether you're going to convert the kilonewtons to newtons, which means that if you change the if this was 2 kilonewtons, then you're going to say 2000 newtons. But my suggestion is that you keep, and this is one of the few exceptions in mechanical technology, that you keep it as kilonewtons. So if this was 2 kilonewtons, then for example the answer here would have been 3.25 kilonewtons, and here it would have been 2.75 kilonewtons. Just make sure that the units that they give you over here, that you keep it the same throughout the entire exercise. Okay, but in this case it's still newtons. So all our shear forces will be calculated in newtons. We will only consider the forces. And we will be calculating the shear forces at A, at B, C, D, and E. Okay. If we think about what the shear force diagram looks like, which normally is asked after, that you have to do it after you've calculated the shear forces. The shear force diagram will look something like this. Okay, where this is A, B, C, D, and E. We need to keep in mind that where this is the 0 newtons line, this one over here, the shear forces on the shear force diagram always starts at 0 and it ends at 0 on the 0 newtons line. So it starts at 0, but then it goes up a certain amount, it goes down a certain amount, goes down another certain amount, down again, and then back to 0 newtons line. So the first and the last values or points on the beam will always be equal to 0 newtons. Okay, so at A, where you've calculated reaction left is 3.25, it starts at 0 and then it goes up 3.25. So to write down the answer for the shear force at A, it's going to be 0 newtons, because we write down the answer even before it goes up 3.25 newtons. Okay. To calculate B, we have to consider any of the external forces, whether to the left or to the right. Now, to the left, it's a shorter distance compared to the right side. So we're not going to consider the distance because we are looking only at the shear forces, nothing to do with distance or meters. So A has an influence on B. So at A, it started at 0, it went up 3.25, and at B it went down 2. So the 3.25 is a positive value because it goes upwards. The 2 newtons will be negative value because it goes downwards. Okay, so to write down the value for B, we consider A and B. And to calculate the shear force at C, we consider what happened at A, at B, and at C. So to calculate B, what happened at A? It was at 0, but then it went up 3.25 newtons, because that's the reaction left. And at B it went down negative 2 newtons. So it's minus 2 newtons, which then equals to 1.25 newtons. Okay. To calculate C, we consider what happened at A, at B, and C. So what happened at A? It went up 3.25. At B it went down 2 newtons, and at C it went down another 3 newtons. So it's plus 3.25, minus 2, minus 3. 3.25, minus 2, minus 3, which then equals to, so I'll check here, 3.25 minus 2 minus 3 equals to minus 1.75 newtons. Remember to write down the value as newton because it was given in newtons. Now what happened at B? To calculate B, we have to check what happened at A, at B, at C, and including D. Or we can work, instead of working to the left, we work to the right. Remember, to calculate the shear force at B, we check whether to the left-hand side the influence of the external forces, or to the right-hand side the influence of the external forces. To the left-hand side, which is A, B, and C, and D, is obviously much more and longer compared to the influence of E and D. So we can work to the left, which would have been plus 3.25 minus 2 minus 3 minus 1, or we can just say to the right-hand side the influence of E and the influence of D, which is plus 2.75, this reaction right, plus 2.75 minus 1. And that's the one that we will use in this case. So it's 2.75 minus 1, which will then be equal to, just want to check here, 2.75 minus 1, which equals to, just want to check here, okay, apologies, we're just going to restart from the end of C. Now we're going to calculate the shear force at D. So we are going to work towards the left-hand side, the sum of the external forces, which has an influence on D. So to calculate the shear force at D, it's positive 3.25 minus 2 minus 3 minus 1, which includes point D. So it will be, the shear forces at D, it's 3.25 minus 2 newtons, minus 3 newtons, minus 1 newton, which then equals to minus 2.75 newtons. Then to calculate E, again we are going to work and check the sum of the external forces to the left hand side. So this is going to be positive 3.25 minus 2 minus 3 minus 1 plus 2.75, because remember it includes that point as well. So it's going to be 3.25 minus 2 minus 3 minus 1 plus, which is minus 2.75. So plus and a minus 2.75, which will make us minus 2.75. Sorry, that one will just not be negative, because 2.75 is going upwards, it will be positive, so that will just be 3.25 minus 2 minus 3 minus 1 plus 2.75, which will then be equal to 0 newtons. That's E. Just rather write it here. Equals to 0 newtons. So this is going to be standard that the first and the last value will be equal to 0 newtons, because the beam, which is in equilibrium, it starts at 0 newtons and it ends at 0 newtons. So at this stage, if it did work out that it starts and ends at 0 newtons, you will have 1, 2, 3, 4, 5 marks for this. Okay. Now we are going to draw the, let's first calculate the bending moment diagrams, and then we are going to draw the shear force diagram and the bending moment diagram. Okay, so next we are going to calculate the bending moment diagram. Calculate the bending moments for point A, or at point A, point B, C, D, and E. Okay, so important with calculating bending moments is that a moment is a force times a distance, Newton times meters. So with the shear forces, we were only looking at the forces, not the distances. Now with the bending moments, we are going to consider the distances as well. So the first one that we are going to calculate is the bending moment at point A. And referring to the beam, it's going to be again the moments which has an influence, the external moments which has an influence on point A. So in this case, A, what is the force applied at A? It's 3.25 Newton. What is the distance up to the edge of the beam? To the left side, it's going to be 0 newtons. So it's 3.25 newtons times 0 meters. The force times the distance. So the force over here is 3.25 newtons times 0 meters, which in the end will be equal to any value times 0 will be equal to 0, but the units over here for bending moments will be Newton meters, because it's a force times a distance, it will be 0 Newton meters. Okay. B, to calculate the bending moments at B, we check what the external moments, how the external moments has an influence on point B. So to calculate the bending moment over here at point B, we add the values of the external moments to the left or to the right side. So to the left side, it's the shortest distance, so it's positive 3.25 times the distance of 2 meters up to B. We are not looking at the 2 newtons at B. It's reaction left, 3.25 newtons times 2 meters. 3.25 newtons times 2 meters, which equals to 6.5 Newton meters. Again, keep in mind it's a force times a distance, so it's Newton meters. Next, we are going to calculate the bending moments at C. So that is the sum of the external moments which has an influence on C, or up to C. So there is a force and there is a force at A and at B. So force A is going to be upwards, which is positive, so it's 3.25 times the distance up to the point C. So it's 3.25 times 4, in brackets, 3.25 times 4, and then plus, because it's the sum of the external moments. So we are still calculating for the bending moments at C. We have considered this moment, RL times 4, but we have not yet considered 2 newtons times 2 meters. Keep in mind this force at B is downward, so it's a negative value, so it's minus 2 times 2 meters. Minus 2 newtons times 2 meters. Pay attention to the plus sign outside of the brackets, but the moment individually is written inside the brackets, because we are calculating the sum of the external moments which has an influence on point C. So for this one, it will be equals to 3.25 times 4, which equals to 13. This is plus, minus, so plus, minus 2 times 2, which equals to, just want to check, it's point A, B, and C, which is minus, the plus times minus is equals to a negative, so that will be minus 4, which equals to 13 minus 4, which equals to 9 Newton meters. Okay, so that is the answer for bending moment at C. Next, we are calculating the bending moment at D. So the bending moment at D, we can work either to the left or to the right hand side. After we've gone past point C, which was in the middle, point D, the shortest distance is to the right hand side. So instead of saying 3.25 times 6 minus, which is plus, minus 2 times 4 plus minus 3 times 2, we will rather be saying now plus 2.75 times 2 meters. So it's 2.75 newtons times 2 meters, which then equals to 2.75 times 2 equals to 5.5 Newton meters. Okay, the last one is the bending moment at E, and this works very much the same as when we calculated the bending moment at A. The shortest distance at point E to the left or to the right hand side is to the right hand side because it's on the edge. So the force over here is 2.75 newtons, but the distance is 0 meters. So anything times 0 will be equal to 0 Newton meters. Okay, so at this stage, to have calculated A, it will be 1 mark. To calculate B, it will be 1 sum times 2 marks for whatever is in the brackets here. C, it will be also be a mark here and whatever is in the brackets there. D, it's going to be the value here times plus a mark for whatever is in the brackets, and E is just going to be 1 mark. So it's 1, 2, 3, 4, 5, 6, 7, 8 marks in total over here. Now that we've calculated the shear forces and the bending moments, we can start by drawing the shear force diagram and the bending moment diagram. Important with this, for the diagram, is there will be a scale given to you to use for the width of the beam as well as the height for the diagrams. So the width for the beam, in this case, it will be 1 meter equals to 1 centimeter. So we will be drawing, where this is 2 meters, it will be 2 centimeters wide. And again, you have to draw the beam above the diagrams on scale. So over here it will be 8 centimeters because it's 8 meters wide. And just to help yourself, draw the beam with the divisions in, which each is a 2 meter interval. That's 2 meters, 2 meters, 2 and 2. Then use a pencil to lightly project the width of the beam going down. Draw this as a construction line going down with a pencil. The scale that we will be using here, which will be given, is 1 meter equals to 1 centimeter. That's why where this was 2 meters, it will be 2 centimeters wide. Next, as I've shown previously, this is roughly what the shear force diagram will look like. And from the 0 newtons line, it will either go up or down as a positive or a negative value. So we want to start with the 0 newtons line. Just keep in mind, you have to check what is the maximum height that this diagram is going to go up so that it does fit on the page. Okay, so we have to check how far does A go up. And over here with the shear forces at A, remember it went up 3.25 newtons. Then you need to check the scale that will be given to you, and in this case we are going to work on a scale, not just the width for the diagram, but also the height for the diagram. In this case it will be 1 newton will be equal to 1 centimeter. So we keep it simple at this stage, 1 newton for each newton that it goes up or down, it will go 1 centimeter up or down. So at A, which is this point here, B, C, D, and E, at A it starts at 0, but it goes up 3.25 newtons. So we need to start with a 0 newtons line somewhere, which at this stage should be the same width as the beam which is drawn on the scale, which will be given to you. So that will be 8 centimeters wide. The lines projected down will be 8 centimeters wide. This will then be the 0 newton line. Label this on both sides as well as point A, B, C, and D, and then this is also E. So where A starts at 0, we have calculated reaction left to go up 3.25 newtons. According to our scale, 1 centimeter equals to 1 newton. So this is going to go up 3.25 centimeters because it's a positive value. From A to B, it will stay on the same height. Remember, to get the marks, you have to label each individual height, which at this stage, reaction left was going at A 3.25 newtons up. So label it as 3.25 newtons going up. Okay, now to calculate B, where it was 3.25 newtons going up, then it goes down 3 newtons. So it goes down 1, 2 centimeters, which according to our shear force diagram, it's supposed to end at B at 1.25 newtons. So measuring from the 0 line, it's 1.25 centimeters. From the 0 going up 1.25, because we went down 2 newtons, which was at B going down 2. So at this point it will be drawn a horizontal line from B to C. Just draw a light line going down there, label the height of this one, which was 3.25 minus 2 newtons, which gives us the answer which we calculated at B, which is 1.25 newton. Okay, next, to calculate the shear force for the diagram at C, we were at 1.25 newtons at B, but then it went down another 3 newtons. So from this point it goes down 1, 2, 3 centimeters, which gives us a value of 1.75 negative 1.75 newtons, minus 1.75 newtons, which is the value for the shear force diagram at C, which is over here already calculated. C equals to minus 1.75 newtons. The next one is at D. So after C it went down another 1 newton, which is 1 centimeter. So it went down 1 centimeter. Just we'll draw this line lightly. It went down from C up to D. It went down 1 centimeter, which stays the same to the right hand side, which is supposed to end from the 0 newtons line at 2.5. Sorry, this is supposed to be 2.75. It's going to go a bit further down, which at D is supposed to be minus 2.75 newtons. So from 0, you go down 2.75 centimeters, label that as a horizontal height and label it as minus 2.75 newtons. Okay, so at this stage, if you've drawn the shear force diagram with the heights, whether it's positive or negative, if you've labeled them according to the correct height and the label, and remember the units, you will have 4 marks. The last mark will be given for drawing in the hatching. This can be as freehand hatching, and also the width of the scale of the beam at the top has to be on scale according to the scale that was given here. So that will be an extra mark if the hatching is included along with the scale for the width, which is drawn correctly. Just keep in mind, as I've explained it, I was working from the beam over here, checking how far it goes up, how far it goes down, down another 3, down another 1, up 2.75. But you've already calculated here the shear forces, which is the value where the diagram lies on the sketch that you've drawn. So here it lies at 3.25. Here it lies at from B to C 1.25. Here it's 1.25. The next one lies at minus 1.75, which is this one, minus 1.75. And then the last one, minus 2.75, minus 2.75. Okay, so you've got 5 marks for the shear force diagram. The last thing that we have to do is to draw the bending moment diagram. Bending moments are Newton meters, so we are going to draw this diagram also in line with our beam, which we drew on scale at the top. Remember the scale is given, so that is 8 meters, which will be 8 centimeters. Those lines you've projected down with the pencil, extend it even further down so that you can draw your bending moment diagram below that as well. If it does not fit on the same page, redraw yourself the beam at the top on a new page, and then draw the bending moment diagram below this. Okay. One thing that you can take note of is that all the values for the bending moment diagram will be either 0 or positive values. Nothing will be negative values. So A is 0 Newton meters, B is 6.5 Newton meters, C is 9 Newton meters, D is 5.5 Newton meters, and E is 0 Newton meters. So those will be everything drawn as positive values for 0 Newtons. So your 0 Newton meters line can be drawn at the bottom of the page, because everything for the diagram will be going upwards. So this is 0 Newton meters. Make sure you write it as Newton meters, not as meters, because with the shear force diagram, everything was in meters and newtons. So with the shear force diagram, everything was in newtons, but with the bending moment diagram, everything is drawn in Newton meters. So on the left and on the right side, it's 0 Newton meters. Also label this as point A, B, C, D, and E. And the scale that we will be working with over here will be 1 Newton meter equals to 1 centimeter. Sometimes, actually most of the time, they don't give the values as centimeter. They will say 1 Newton meter equals to 10 millimeters. but we know 1 centimeter equals to 10 millimeters. So you can simplify this the way that they give it to you. For example, in this way, you can just simplify it for yourself to be in centimeters to make it simpler with the measurements, with measuring them and drawing the diagram. Okay, so that's the scale for the bending moment diagram. Again, remember, we're starting at 0 newtons and we are ending at 0 newtons. A over here starts at 0 newton meters, so you make yourself a dot over there. B is 6.5 newton meters. The scale that we use is 1 newton meter equals to 1 centimeter, so that 6.5 newton meters will be 6.5 centimeters. So at B, from 0 it goes up 6.5 centimeters. We label this as 6.5 Newton meters. Make sure you label it as Newton meters because the value is Newton meters. Even if you write down 6.5 but only newtons, this mark will not be allocated. Make sure that the bending moment diagram, everything is drawn in Newton meters. The shear force diagram, everything is drawn in newtons. Okay, so from A to B, it's going to be a straight line from 0 newton meters to 6.5 newton meters. The next one is to plot the point for C. C over here is, C we've calculated as 9 newton meters. So from the 0 line, which is at C, start at the bottom, it goes up 9 centimeters. And that will then be a straight line connecting from B to C, which is 9 Newton meters. The next one is to calculate or to plot point D. D we've calculated it to be 5.5 Newton meters. So from the 0 line at the bottom, 5.5 going up, that is the point for D. Label that as 5.5 Newton meters. That was D, and E is the last one, which we've calculated to be 0 Newton meters, which is from 0 Newton meters, a straight line to the 5.5. Okay. So at this stage also, your diagram is supposed to look like this. If you've correctly labeled 6.5 Newton meters, 9 Newton meters, 5.5 Newton meters, as well as the 0 Newton meters, you will have 4 marks. 1, 2, 3, 4. You also get a mark for drawing hatching in. This can be done freehand. If you've drawn the hatching in as well as the width of the diagram is drawn correctly, you will get another mark. So it will be 1, 2, 3, 4, 5 marks for the shear force diagram. Okay. So those in total, so it's 2 diagrams, it's 5 plus 5. Bending moment diagram is 8, so it's 18 plus the 8 marks for the moments of reaction left and reaction right, plus the 5 marks for the shear forces. That will give us a total of 31 marks for this calculation. Last advice that I can give you is just read the question carefully. Whether they do ask you to calculate the reaction left, the reaction right, shear forces, the shear force diagram, as well as the bending moments and the bending moment diagram. Sometimes they ask only for the calculations and not for the diagram. Or they only ask for the one calculation, for example, the shear force diagram, for the shear forces and then the shear force diagram, but not the bending moments or the bending moment diagram. And then the learners tend to unnecessarily waste time by calculating the bending moments when it was not even one of the questions and it doesn't count any marks. So read the question carefully and do the steps or exercise this as much as possible, because there's no specific formula for doing this exercise. It's rather just doing an exercise one after the other, getting used to what steps you have to follow and making sure that the units are correct throughout the entire calculation or exercise.